welcome to my keynote about functional programming and Kotlin, I think, which is nicely in line with our nice announcements we just had. I'm already a bit announced. What's maybe also interesting to hear is that, well, I call myself senior software engineer with all my gray hair and 20 years in the industry, as it's called. I dare to use this name. In my daily job, I try as much as possible to keep my hands in the dirt, because this is where the real thing is happening. Also train at Xebia Academy, which is already announced, where I give a variety of courses, mainly about Kotlin, of course, where I help developers in all stages of their Kotlin journey, from beginner, intermediate to advanced. So I see quite a lot of environments. I see how Kotlin is used, which is very interesting. When you look at my career, at least on the GVM, it started out with Java. Then about 10 years ago, I switched over to Scala. And since about 4 to 5 years, I'm exclusively programming in Kotlin. Well, the reason I tell it is because later on this might become a bit more relevant, especially my times with Scala. Okay, so this was about me. I would also like to know a little bit more about you. So who of you considers himself an intermediate or advanced Kotlin developer? Okay, so this is what I would have expected, more than half. That's great. Who of you has heard the word Monads? That's even more, that's great. Also, if you're not an intermediate advanced developer, you've heard of the word monad. Who knows exactly what a monad is? That's definitely a lot less, which I also would have expected. And who of you wants to know more about functional programming? That's good, that's good. So most probably there is something interesting in it. So then let's, without further ado, let's hit the road and start our journey, which hopefully will be a transforming one. And we start out at the swamps of imperative programming. And of course, we hope that it will end up at a nicer place than at the swamps, right? Okay. When we differentiate the programming styles we have in the world, then we actually have two big kind of schools, so to say. We have imperative programming. Imperative programming heavily relies on variable declarations that are mutated along the way, and once you've reached a certain state, then just you return whatever you want to return. So the language constructs we use in Kotlin are vars, loops. We also use a lot of mutable data structures like collections and objects, and quite a few return statements, here and there return statements. So, of course, the piece of code you see here is a truly nice example of imperative programming. So that's for one. On the contrary, we have another way of programming. So semantically, it's exactly the same. So these two pieces of code produce exactly the same result. The other school is expression-oriented programming, which is more thinking in functions. It's thinking in input and output. The constructs we use there are mostly immutable features of Kotlin, like data classes, vals. We use mostly expression constructs, which means whenever we call something, we get something back, instead of a statement which just produces some side effect. We also rely on these higher-order functions on top of collections or just standalone higher-order functions. Well, what's really fundamental about these two different kinds of styles? It's about how we think about code. In the first style, we think about mutating data, about side effects. Whereas in the expression-oriented style, we think about transforming data. We think more input, transformation, output. And this output can again serve as input, transformation, output. Once I personally started to embrace this expression-oriented programming, my skills as a developer really got a tremendous boost. And that's also quite easily to justify why that is, because you simply write better software if you use the expression-oriented style. These are some reasons. First of all, that's what you also can see. Our code looks concise or more expressive, whereas on the imperative part, we have these variables that we loop through and do stuff. Now we actually program on a higher abstraction level, telling we are filtering, we are max by, so our code gets more expressive. Because we use expressions, so everything that we do returns something, we can say that our code is also more deterministic, and when something is deterministic, you can easily test it. Then some sort of side effect, and then you have to figure out what has actually changed. Here, by having only the reply, we can say 99% of the cases, this is the thing that has changed, and this you can test. which also actually makes our code much more scoped. So the scope of our code is basically the function where something goes in and out. Whereas in the imperative part, we have some variable declaration here, a lot of stuff happens with the variable, so the scope of our code is much larger. This all leads to the fact that we also then get code that is way more easier to reason about when we use the expression-oriented way of programming. So, I really can promise you, should you not yet program this way, then I invite you to do this for the next 2 weeks, and I promise you the grass is really greener up there. We've left these swamps, and I think now we find ourselves in an environment which is quite nice, the fruitful valley of expression-oriented programming. Okay, so far so good. However, the real world isn't always as pure as this paradigm goes. Sometimes we still have to deal with mutable stuff, okay? Like the code we have here. Let's quickly walk through it to see what we do, because it's quite messy, right, when you look at it. So first we do something with some initialization of a REST client, then we do something with file, well, then we fetch data with the REST client, and eventually we output the fetch data to the file in the format of a CSV. And in the end, we do some resource handling. Because we have these mutable constructs, you might think, okay, I can't really use an expression-oriented style. I have to do just assignments and side effects. That is true. However, when you rely on Kotlin scope functions, you can kind of bridge these two worlds quite nicely. So for instance, here we use this REST client, and then we grouped operations we execute on REST client by means of this apply function. This has two benefits. As said, first of all, we group stuff, and second, we also isolate the mutable pieces that we execute on REST client. Same is true for let. Also, it's also a nice way to indicate there is a side effect. So you kind of hinted, hey, in this part, some side effect is happening just by looking at it. And also run, I think, is on file is a beautiful example of not even having to expose a variable that could be used maybe later on in refactoring to do stuff in a wrong manner. Here we fully isolate the access to file, and everything that is happening is in between. So when you do refactoring, the chances that things break are much lower than that. So I consider these scope functions a good way to, as said, to bridge the mutable world with the more expression-oriented world. Because what we've seen is whenever we apply the scope functions, we again get actually expressions. It returns something again. So we moved a bit further on in our valley of expression-oriented programming. Okay, but when we look around, we're still in a valley, right? So we want to climb up. So now our PO comes to my desk and says, it's nice that we output the stuff to CSV, but let's do something crazy. Let's output it as CSV, as TSV, tab-saturated values. Well, what I could do is I could copy-paste it and then execute as TSV, which is kind of silly, right? We don't want to have so much duplication. But what kind of structure can I come up with that I get rid of the duplication? In order to do that, there's a very simple trick we can apply here, which is first, let's look at the code which we duplicated, because this piece of code becomes our generic control structure. Then we look at the part that varies, and then we actually use this varying part to extract this into a function to make it more configurable. And in order to do that, we have to closely look at the signature of this varying part, what goes in the varying part and what goes out in the varying part. And this is actually where we define our function. As you can see here, two-line, developer goes in, the string goes out. And then we use this function at the designated place to make our method much more pluggable. And now we're flexible, right? We can actually output it to every format we can think of. And this is basically when we've encountered the value of higher order functions. A nice practical example I see not widely used is, for instance, with testing. When you do some data testing, often you're quite having a lot of lines of code simply to prepare test data and clean it up after your test. So a significant portion of your test often is dedicated to that, like we see here. This is all, again, duplication. And of course, because you're writing tests, we not apply the most craziest engineering principles, but still, when you test code, this can be some sort of liability, can become a liability. And also here, quite simple. Let's look at which part we duplicate, extract the rank part into a function, and off you go. Which has two benefits. First of all, we have code reuse. But second, we also now can really focus on what's really relevant in our test, on our conditions. So, once we embrace these higher order functions, we've reached abundant heights of higher order functions. So we climbed up a little bit. Further, and we now don't only have nice green grass, but also a little bit of view. Okay, so the higher order functions that we just created, they kind of lack some abstraction that we can combine them with other higher functions to create new valuable results. So what we basically lack is something which is called composability. Okay, when we look at the very first example we saw in this presentation, we see that this code with the collections nicely composes, right? We can apply these higher order functions in order to produce a result, chaining them together until we are satisfied. So apparently these characteristics of this collection container, this construct of a collection, in combination with these higher order functions, allows us to be composable. Now, it can be very interesting to dig a bit further and figure out, okay, what kind of fundamental aspects govern these characteristics? Because if we find them, then maybe we could use these principles beyond collections to create other data structures that are composable too, right? And this is basically when we enter the domain of category theory. And as you can see, it's not a hill, a valley, it's a mountain. And mountains allow you to go very high, but they also give you the chance to fall very deep. So what is category theory? Category theory is the theory of mathematical structures and their relations. Actually, a one-liner. It's not really related to software. It's when we kind of dig deeper with the principles we've shown before, then we actually end up in this theory. And this is also, as said, a danger zone. And as you also can see, in this danger zone, we see these weird words, but the monad is definitely one of them. Well, why is it a danger zone? The reason is that because academia kind of managed it to create such confusing terminology, then we try to port and interpret in software, which is really far-fetched from something you can relate to the real world. So most of the time, either developers are scared of, because when you stand at the beginning of this mountain, look up, the only thing you see is mist, right? Some of us, they kind of went through these clouds, and then they stand on top of the mountain. And, well, the view is quite nice there, but on the other hand, you're quite detached from the real world. You're a bit over the top. And this is, in that sense, also quite a lonely place. It can also be quite cold and windy. So, I think in both cases we fail to unlock the power that lies within these abstractions. And the rest of the presentation, I will do my best to kind of blow away these fogs so that we all can kind of see the value that gives us, but also the pitfalls that are associated with them. Okay, well, some of you ask, you've heard the term monad. Some of you exactly know what it is, quite a few part of this group. We all use monads, that's kind of interesting thing. The way I like to look at monads is, I like to describe them as containers, right? Containers are kind of wrappers that can contain things, and you have different kind of containers. You have containers with air conditioning, you have containers that are sealed, you have the different kinds of. But in the end, they just contain stuff. That's basically it. And to start with, also to kind of take away some complexity, let's look at these monads in the shape of collections. And what we try to look at is not really what collections can do, but more what the container collections make so special that we get this composability. Okay, what kind of characteristics does it possess for composability? Let's start out with our first one. So if you can combine certain collections, this is what you do here. We have a list, and then we combine it with another list. What we get is, well, a collection with all the items of the two other lists. Kind of, not that interesting. In academia, they managed to describe this characteristics as a monoid. I think it's quite a silly name. I would have loved it if they would have called it, for instance, a combinable. I kind of can relate a combinable to what is happening here. A monoid is just a weird name. This is the interface of a monoid. Two methods, so you can create an empty container, like an empty list, and you can combine lists, and instead of having then a list that contains one element of its, so that when you add a list to a collection, then you get an element of a list. No, we just get actually a new list with all the elements of both combined. That's one. The second one is when we can transform elements of a list, we use, for instance, the map method. So we have our container with the items in it, then we map over them, we turn red into yellow, and in the end we have the same container that contains a transformed element, like you see above. In academia, they managed to describe this as a functor. I would have loved the term mappable. I kind of would understand, oh yeah, you map stuff. Very simple map function, functor. The third one is, last but not least, the one that is, you also all know, but that's kind of the one that gives you interesting powers. Before we look at an example, let's look at our data structure. We have a developer, and we have languages, and what we'd like to extract are all the languages of all developers. If we now would use our map method, well, we would end up with a list of lists. But that's not what I want. I want to have all the languages of these developers. Well, you might know it, then you use flatmap, right? What does flatmap do? So each element you transform, that results again in a container. We make sure that at the end, the additional container introduced is flattened out. That's basically it. And when you combine the capabilities we had before, so the functor, the monoid, with this flat map, then we get basically a monad. All combined together. When we can combine things, create empty containers, it's a monoid. When we can map over things, it's a functor. And as I said, all these capabilities are part of the monad where we have this flat map method. Not very interesting in that sense. Still, I guess, I hope, easy to follow. Well, you all know collections, which are monads, as we see now. But you also know other monads, like, for instance, optional. So what is optional? If you clearly define what optional is in this category theory lingo, then you could say that an optional models the effect of optionality. So the optional monad or data type models the effect of optionality. I explicitly use the word effect because this is something you definitely will hear more often today. So let's see, is it a monad? Let's check. Well, you can create an empty optional. That's possible. You can map over an optional, but the map here is syntactically the same like in collections, but semantically it does something else, right? It only kind of converts the element if the optional is not empty. We call it map, but something else happens. The same is true for flat map. If you flat map a collection, then it flattens out the outer collections. Here, again, flat map would only be triggered if I wouldn't have a none. And if then in my resulting computation I get another optional, it would make sure that we don't get optionals of optionals, but only one level, one optional with its value in it. Okay. These are all the monads you know. I'm really sure you know more. Like, for instance, a future. We use a mono, which is from the Reactor library, but there are many different of these data structures that do basically exactly the same. What do? A future models the effect of latency, right? So you can do non-blocking I/O, for instance. Is it a monad? Let's check. We can say mono.empty. Works. Say we call some APIs to return monos or whatever, observables, unique, complete with future, doesn't matter. Then we can map over the results. And also here, map is different than from a collection, because map will be triggered once I have gotten a reply for my remote call. Syntactically the same, but semantically different. So where does flat map come in? If I try to call two APIs, and because everything is asynchronously, then, well, I have to use flat map in the sense that I get something back, and this input I will use for my next method call. But I don't want to end with a mono in monos, right? I just want to end with a single mono and a value. And this is why I have to use flat map. Okay. So just to recap, what is this terminology good for? Well, not much, unless you're a scientist. I think it's really just in our way. But okay, that's the way it is. And just introduce new terminology probably makes the thing even worse, but so live with it, I would say. And as said, the advantage is that we get this composability ability with these data structures. So once we've tasted actually composability, why not just make other structures also composable? Like, for instance, error handling. There's also a nice talk, by the way. When you want to get all the details, then this afternoon is a nice talk about functional error handling. For now, just keep it at a conceptual level. So this try-catch, I think we agree on that, doesn't really compose, right? It's just different kind of code blocks that cannot be kind of nicely combined together. So you want to make it more composable? Well, you need a monad. And the nice thing is there is already a monad in the standard library, which is a result. And you might have used it before. This is how result more or less look like. So a result models the effect of having an exception or a value. Cannot have both, it's either or. This is what it models. And as you can see, we have a map and a flat map method. So apparently we can compose stuff. This was our initial example. So now we can say, using run catching, who has used run catching before? Okay, about half. So what run catching does is you can give it some operation, and then it will return a result. And when your operation failed, you get a result that contains an exception, otherwise you get a result with its value. And as you can see, from then on, we nicely can compose. Well, this is Carl, by the way, and I think he has a good point. I mean, how do I know that this client getDev by name throws an exception? I mean, it's not in its method signature. I know because I do some REST call, there might be some I/O exception involved, but it's not in the method signature. So how do I know that to wrap run catching? Do I have to from now wrap everything I do in run catching? It's probably not such a good idea. So in order to kind of be explicit, it might be an idea, and whether it's a good idea, I really leave for now somewhere else, but it might be an idea to kind of make things explicit. So instead of returning our developer, I return a result of developer. So when someone calls the API, knows, oh yeah, when you call the API, you might get back an exception. So do something with it. Which of course is not totally in line with the fact that Kotlin only has unchecked exceptions, right? So, and this is something we're also going to explore a bit later on. But for now, let's just be puristic and say, I want to have very clear deterministic magnet signatures, and if you throw an exception at me, then I also want to know it. This is what you do right here. Well, and then we get code like that, so that each time I return something, I would wrap it in a result, and then I do my compositional magic to get things done. Okay, so far so good. Let's extend our example. So let's add another method like getStats4, statistic for a language. You also have to come up with some examples in presentation, and this is what I came up with. And in order to simply call these three services, one after the other, without even exception handling, so in the previous example, we had to handle some exceptions. Here we just pretend, if there is exception, just let it be in the result, and we continue. The only thing we do here is calling these three services. And as you can see, there is, again, this flat mapping involved. Because otherwise, I would get a result in a result in a result. This is not what I want. I want to have one result at the end. And that's why I have to use flat map. And yeah, I promise you, I think the average Kotlin level in this room is so much higher than in the rest of the world, and the really common places where, yeah, even such concepts are really way too far. If your peer programmers that are maybe not as mature in Kotlin as you see all this flat mapping, they might be kind of be put off. Like, I don't get it. So, can we do better? Well, I think now it's time to introduce you to Arrow. As said, I keep it only at the conceptual level. I'm not going into details. There will also be great talks by Alejandro, by Simon this afternoon. So join them and there you get more of the details about Arrow. What is Arrow? Arrow is a beautifully crafted library that gives you access to all these functional concepts in a very, very accessible way. That's what I have to say. The beginning of Arrow, it was a port more or less from Scala, so we're highly inspired by Scala, which was, we really could read what Scala did, and it was a bit disconnected with Kotlin, because it was a port. And now you see, as it evolves, they really do a great effort to align it as much as possible to make it feel like native Kotlin, even so you use some of these powerful constructs. So I really call it a jewel. So first, it has flexible structures. At the core, it's called effect. We've heard it before. And these effects you actually can apply to very different data types to also create composable monadic behavior. This is for one. They also offer you a variety of monads. And on top of that, they also, as said, make it for you quite easy to work with these data structures. So what they also offer is something that's called monad comprehensions. These are also things that are taken from functional languages like Scala and Haskell. How does such a monad comprehension look like? Well, in Kotlin, we don't have language features for that. Functional languages have features for that. In Kotlin, we have a very powerful construct, which is this function literal with receiver. That's the official name of it. So what we do here is we have this result. Then we get this effect scope implicitly. And on effect scope, we have this method bind. And bind basically allows us to retrieve the result of a result in case it's a real result, not exception. So that I can program in a sequential way. So semantically, these two snippets, top and below, is exactly the same. It's just made more accessible to use. That this result doesn't get too much in your way, forcing you to use these complicated flat map structures. So I think, and also if you're not that mature in Kotlin, this bind might be a bit weird, but I think the rest of the code is quite okay. It goes even further. In the latest version of Arrow, and with the advent of these context receivers, you might have heard of that. There's also a nice talk this afternoon by Leandro, who will tell you all about context receivers. They made the signature even more standard Kotlin. So also here, semantic is exactly the same. Saying context effect allows you to kind of hide that there is also another result you might get back, like a throwable, but it could also be any other data type. Then the only thing you have to do is bind. Okay, so far so good. Are we there yet? Not really. Because in the real world, I need more than a result. In the real world, I need reactive behavior. So I need a future, mono, uni, whatever you call it. And of course, I still want to be explicit because I want to know whether I get exception or not. And well, if you're anyway doing stuff with these monads, why not use option? That's a type from Arrow, which indicates whether something is has a value or not. And if you go down that route, then, well, you get code like that. And the only thing we do here is basically call these three services. And as said, you have map many times, but each time, depending on the monad you use, it has a different meaning. So map is not equals map, and it's the same word, but it has a really total different meaning. And should you encounter yourself with such code, then congratulations. You were capable to turn your code base into a container terminal. And you know where you are. You're here at this crane, shifting around these containers. Whereas your boss wants you to write your business logic, not shifting around containers. And unfortunately, I have to tell, I've been there. And it's not much fun. I've had this in Scala. Scala gives you better ways to deal with that, to be fair. But still, it feels like shifting containers around in a container terminal. Losing kind of touch with what did I want to try to achieve in the first place? So maybe you can say, why not use these monad comprehensions? Maybe they make things easier. Well, the point is that these comprehensions only work with one effect monad, so to say. There is something which is called monad transformers. What is a monad transformer? Again, a fancy name for something very simple. A monad transformer is a method on an outer monad that directly transforms a nested monad inside. So instead of calling map, we now could say, we could call map t. And then we would directly convert the result that is contained within the monad. Okay? This is only there for 2 levels of monads. Doesn't really help us. And Kotlin also misses some features to apply them. And anyway, you don't want that. You get these kind of things. Flat map t, flat map t, flat map t outer. Doesn't make your code much more fun, so to say. Okay, so the question is, can we kind of reduce our code to 1 monad, even though we need 3? I think we can. First of all, mono. Who's using these reactive building blocks, by the way? A few of you? Okay. I would strongly advise you stop doing that. Because in Kotlin we have coroutines that makes it so much more easier to use. And should you not know how to do that, in 2 weeks from now we have a nice Kotlin training day where you learn how to do that. It will be a revelation, I promise. So here, mono is gone. Second, do we need option? If you look at Kotlin, we have already this concept, we have nullable types. So let's use that. And when you then brought it down to that level, I think your code is still kind of manageable again. Okay, so now we have explored the lonely peak of monadic mist. Is this the end of the talk? It's not really a happy end, right? So let's try to kind of draw conclusions. Which actually brings me back to what kind of monad is good enough for your code? When do we go too far? When don't we use enough of them? Which brings us back to why the question, what is good code? Well, many books and blogs have been written about that. I keep it very simple. I think good code reflects the domain you're in. So when you're at a pet store, and in your pet shop, then your code should look like a pet shop. The same is true for an investment bank. If you can relate the things in your code to what the business you're in, I think you've written good code. Which means that non-domain abstractions should be as less as possible. And if they're there, they should have a very clear purpose. And to say it in a one-liner, if you PO, scan through your code, and he kind of understands what's going on, I think you've written good code. Because if a non-technical person kind of understands what's going on, everybody else will understand it too. You also could say, well, if your code looks like this, it's probably not good code. Unless your company is this container terminal. Okay, so just to round up, what I would like to do is get all these method calls and kind of put them in perspective of a whole application. And a very traditional one with layered, no orthogonal stuff, just layered application. See how these monad affect actually our whole call chain. Starting out with some data access layer, then we have some service layer, some API layer, and eventually you also need something like global error handling to get really good results out. So what we have used here is these results. But by the way, in the API layer, we kind of convert the result to an exception, assuming Spring Boot, which doesn't really support results. You could make it support results, but let's just assume vanilla Spring Boot, which then would actually return our error result. And if you look through all the other layers we have, we don't really do anything with the exceptional case of result. We just kind of pass it on. Don't do anything with it. So if we only pass things through, why do we have it? If you just don't have it at all, well, I think your code is more readable. These exceptions will produce our error result, so just why not have this case where you throw stuff and the exception handler just make sure you get error responses. Well, for 95% of the cases, I think this is perfectly fine. Well, of course, there's also the other 5%. Let's see. So when we have normal results, then do we need monads? Probably not. If you just have some technical exceptions, we anyway can transform and produce something else. I would say throw them through, give an error result. However, if you have some API calls that result in different return types, then it might be useful, especially if you can recover from that error, to give an explicit interface how to handle this particular case. Then I can decide. So here I would say it makes sense. So for instance, for database stuff, well, why do you need a monad? When there is something wrong, throw and your user gets something is wrong. However, for instance, for API calls, I, by the way, wouldn't use result. Looked at result many times, but dealing with exceptions as exceptional cases in results, it's not very great. Either, which is very close related to result, I think is the good type, because either gives you the possibility to not only have exceptions, but any other data type. So you can get either an API error or a language. And then our business layer, service layer, kind of, first of all, knows that there can something go wrong, and has also an API to clearly deal with the corner case. And I think once you apply the cases where these monads shine, instead of just throwing them at everything in your code, I think then you've reached the prosperous alm of functional common sense. And this is the mix I've seen really working. It's not pure, I know that, but it works. And I've done pure stuff which just got a lot of complexity and headache. So the mix I've shown here today, I've seen really working in practice very well. Which brings me to the conclusion of my talk. Well, we all know this sentence. Making things simple is hard. You know what's even harder? Keeping things simple. That's what you see so many times in practice. It starts simple with this small application. It grows, all of a sudden, there's a lot of headache. So keeping things simple is a real challenge, especially when people like you that are hungry for advanced Kotlin and want just to throw these advanced concepts at their code. So my pledge for today, and actually also for my remaining career in that sense, is use these advanced things to make things simpler, not harder. Challenge accepted? We'll see. Thank you.